right now, your seamless, your weightless cloud connection is hanging by a literal thread, or, well, more accurately, an 8-pin twisted piece of copper.
Yeah, which is kind of wild to think about.
It really is. I mean, we talk about the internet like it's
Ah.
this invisible, magical ether, you know?
Yeah.
You open your laptop, you click a link, and instantly you're looking at a live video feed from across the planet. We just constantly use this technology without ever really thinking about the physical reality holding it together.
Right, it's like a necessary illusion. You have to break that illusion if you actually want to understand how our modern infrastructure survives. Because behind every instant download and every flawless cloud sync, there is a very grounded, intensely manual physical reality.
Exactly. So for you, the listener joining us on this custom deep dive today, we are going to completely shatter that illusion. Our mission today is to demystify the physical toolkit that network technicians actually use to keep this supposedly wireless world functioning.
And we're pulling directly from course materials from Professor Metzer's CompTIA A+ certification training, specifically focusing on the network tools section.
Right. And what we're going to find out is that before any data can flow into the ether, the physical pathways literally have to be forged by hand.
Yeah, you have to physically connect point A to point B. And depending on the environment, that means relying on a highly specialized set of hand tools.
Okay, let's unpack this because I want to know exactly how those physical connections are made. Like, if I'm handed a box of bulk cable that has no ends on it, just raw wire encased in a plastic jacket, how does that actually become a conduit for the internet?
Well, assuming we're working with standard twisted pair copper cable, you know, the kind you see plugged into the back of a desktop computer or a Wi-Fi router.
Right, the classic Ethernet cable.
Exactly. You need to attach the appropriate connector to that raw wire. And the foundational tool for this is the cable crimper.
A crimper, so we're talking about attaching that chunky, clear plastic plug, the RJ45 connector.
That's the one. The crimper is basically this heavy-duty hand tool, and its entire purpose is to permanently pinch that RJ45 connector onto the end of the raw cable.
Yeah.
But the mechanical action of how it achieves this is what makes it so vital. Inside a brand new, uncrimped RJ45 connector, the tiny metal copper contacts aren't flush. They're actually sticking up just a little bit.
Oh, really?
Yeah, and at the bottom of each contact are these very sharp, pointy teeth.
See, the course materials emphasize those sharp ends, and it's almost like a tiny, extremely precise vampire bite. Like the pins have to pierce the skin of the wire perfectly in order to drink the data blood, which is the internal copper core.
I mean, that is a highly visual way to describe it, but mechanically, yeah, that is precisely what's happening. When you insert the dressed wires into the clear plastic plug and squeeze the handles of the crimper, the tool applies this immense, even pressure. It forces those raised metal teeth down, pressing them completely through the plastic insulation surrounding each individual wire. They don't just touch the wire, they literally bite into the raw copper inside to form a permanent electrical bridge.
And it does something else simultaneously, right? It isn't just about the electrical connection.
Right. Secondary to the electrical connection, the crimper also pushes in a small plastic wedge near the base of the connector. It's called a cable stay.
Okay, a cable stay.
Yeah, and this wedge bites aggressively into the thick outer jacket of the main cable. It basically acts as strain relief.
Oh, I see.
That way, if someone trips over the cable under a desk, the pulling force is applied to the thick outer jacket, not the really fragile, tiny copper wires inside.
That makes total sense. But I do have to push back on the reality of this workflow a little bit.
Okay, sure.
If you're setting up a network, doesn't it seem incredibly tedious to manually sit there, strip the jacket, untwist the wires, line up 8 tiny color-coded strands in the exact correct sequence, and crimp on these ends by hand? Like, why wouldn't a technician just buy pre-made cables in whatever length they need?
What's fascinating here is that custom scalability relies entirely on this manual precision.
How so?
Well, when you're wiring a massive corporate office or a huge data center, you aren't dealing with simple 3-foot connections. You might have a server rack that requires a cable run of exactly 82.5 feet to reach a specific patch panel.
Oh, right. And you can't just buy an 82.5-foot cable off the shelf.
Exactly. You'd have to buy a 100-foot cable, and that leaves you with over 17 feet of slack.
Just dangling there.
Yeah. Multiply that 17 feet of slack by 1,000 cables in a single server room, and you suddenly have a catastrophic, tangled mess. It's what technicians call cable spaghetti.
Wow, cable spaghetti.
Yeah, airflow gets blocked, servers overheat, and tracing a single wire becomes completely impossible. Crimping by hand allows you to pull the exact length required, leaving the infrastructure completely pristine.
Which perfectly sets up the other major foundational tool for copper wires. Because you aren't always crimping an RJ45 connector onto the end of a wire, are you?
No, not at all.
Often, you're wiring the building itself. You're terminating those raw cables into the permanent architecture of a data center using a punch-down block.
Right. Picture the back wall of a telecom closet. You might have thousands of raw cables emerging from the ceiling, representing every single wall port in the entire building.
That sounds overwhelming.
It is. So to make managing all those connections possible, technicians terminate them into stationary plastic blocks with rows of metallic grooves. These are often called 110 blocks.
Okay, and the tool used for this is literally called a punch-down tool.
Yeah.
How does it differ from the crimper we just talked about?
Well, instead of squeezing a connector onto the wire, the punch-down tool forces the wire down into a V-shaped metal blade on the block.
So you just press it in.
You lay the raw wire over the groove, position the tool, and push down hard. The tool is actually spring-loaded. When it reaches the exact right amount of pressure, it fires downward with a loud snap.
And the V shape of the groove is what actually cuts the insulation to make the copper contact.
Exactly. The groove displaces the plastic insulation, wedging the raw copper tightly against the metal. And the best part is that the punch-down tool has a tiny scissor blade on one side.
Oh, neat.
Yeah. As it punches the wire into the groove, it simultaneously shears off the excess tail of the wire, so it gives you a flawless, flush termination in just a fraction of a second.
But the source material flags a massive caveat for anyone using this tool.
Yeah.
The technician has to be obsessive about the twists in the wire.
Oh, absolutely. Obsessive.
They can't just untwist 3 inches of wire to make it easier to lay into the block. They have to maintain the twists as close to the punch-down point as physically possible. Why is that?
Because the primary defense against invisible interference in an analog cable is the physical twist of the copper itself. Yeah. The cables are called twisted pair for a highly scientific reason. They utilize differential signaling. The equipment sends the exact same signal down 2 intertwined wires, but with opposite polarities.
Oh, so they're basically mirrors of each other.
Right. And because they're tightly twisted around each other, any ambient electromagnetic noise, say, from a fluorescent light ballast or a nearby power cable, it hits both wires equally.
Okay, I see where this is going.
When the signal reaches the other end, the receiving equipment compares the 2 wires, calculates the difference, and perfectly cancels out the noise.
That's brilliant.
It is. But if a technician untwists too much wire before punching it down, that unshielded segment acts like an antenna. It absorbs interference that can't be mathematically canceled out.
Man, it's a wild example of how purely analog physics, like the literal geometric shape of a twisted copper wire, can completely dictate the speed and reliability of our high-speed digital reality.
A single sloppy punchdown can degrade an entire gigabit connection.
Okay, so imagine this scenario. You've painstakingly maintained your twists, you've punched down thousands of wires into these massive wall blocks, and you've crimped thousands of vampire-bite RJ45 connectors out on the office floor.
Sounds like a busy week.
Right. But someone forgot to label the cables. You're staring at a massive haystack of identical gray wires in a dark closet, and you need to find one specific connection from the CEO's desk. How do you find the needle?
That is where you bring out a 2-part tool, the tone generator and the inductive probe.
Okay.
This is essentially how technicians track the invisible paths of wires across vast physical spaces without pulling them back through the walls.
The source compares it to playing Marco Polo, but I want to understand the actual physics of how this probe works.
Step 1 involves the tone generator. You take the small battery-powered box and plug it into the wall port at the CEO's desk. The generator sends an alternating electrical current down the copper wire.
Got it.
This current creates an audible analog frequency, a literal screeching tone.
But wait, we can't hear it just by standing in the room, right? I mean, the copper isn't a speaker.
No, the copper isn't a speaker, but that alternating electrical current creates a very weak electromagnetic field that radiates just outside the plastic jacket of that specific cable.
Oh, fascinating.
And that is where step 2 comes in, the inductive probe. You walk back to the massive closet of cables, turn on the probe, and start waving its tip through the bundles of wire.
And it just detects that specific radiating field.
Exactly. The probe acts as a tiny, highly sensitive antenna. Because it relies on electromagnetic induction, you don't even have to touch the bare copper.
You just wave it around.
You just brush the tip against the outside of the plastic jackets. As the probe gets closer to the electromagnetic field created by the tone generator, a speaker on the probe starts converting that invisible field back into sound. The closer you get, the louder the screech.
So the probe literally screams when it finds the matching wire.
Yeah.
Marco has found Polo.
Yep, you've isolated your cable.
But finding the wire doesn't mean the wire is actually capable of carrying a signal safely, right? How do you verify the integrity of the connection you just found?
Once you locate it, or even once you finish crimping a new cable, you have to verify your work. That requires a cable tester.
A standard Ethernet cable has 8 individual pins. And according to the materials, a basic cable tester is primarily performing a continuity test.
Right. A continuity check is the most fundamental diagnostic you can run. You plug one end of your wire into the main tester and the other end into a detachable remote unit.
Okay.
The tester simply sends a small voltage down pin number 1 and checks if it successfully arrives at pin number 1 on the remote side.
And it usually just counts them off with LED lights, right?
Yeah.
Pin 1 to pin 1, pin 2 to pin 2, sequentially all the way to 8.
Yeah. If a light doesn't illuminate, you know the connection is physically broken inside the jacket, or maybe a pin didn't pierce the copper during crimping.
What if they light up out of order?
If the lights illuminate out of order, say, the tester sends on pin 2 but receives on pin 3, you accidentally crossed your color-coded wires inside the RJ45 connector.
Let me pose a scenario based on an analogy.
Sure.
Say a continuity tester gives you all green lights, 1 through 8. Everything cycles perfectly. Some people might assume that guarantees a flawless high-speed network connection. But isn't a continuity tester just checking if the plumbing pipes are connected?
If we connect this to the bigger picture, that is the perfect way to look at it. Just because the PVC pipe correctly connects the bathroom sink to the sewer main does not mean the pipe isn't full of cracks leaking water everywhere.
So it verifies the path, but not the quality of the journey.
Exactly. Continuity testers are completely blind to signal degradation. They cannot tell you if you untwisted too much wire at the punch-down block, causing massive electromagnetic interference.
Right.
They can't tell you if the copper is degraded or if crosstalk is corrupting the data. They only answer one binary question. Does an electrical path exist? Yes or no?
So if a continuity tester is just a basic pipe check, how do technicians diagnose the invisible cracks? What happens when the connection is completely invisible, like a failing Wi-Fi network?
Well, wireless networks are notoriously difficult to troubleshoot because you can't physically trace the wires. We've all experienced having full Wi-Fi bars on our phone, but a terrible internet connection.
Oh yeah, constantly.
To diagnose that, technicians use a Wi-Fi analyzer.
So if my Wi-Fi analyzer is already showing me the active 802.11 wireless channels in the building, what makes it so useful for troubleshooting?
A Wi-Fi analyzer provides a visual map of signal overlap. In a dense apartment building or an office park, multiple routers might be broadcasting on channel 6, for instance.
Okay.
A Wi-Fi analyzer will show you exactly how loud those competing networks are. It reveals the signal-to-noise ratio.
The source material notes that if you're far away from your access point, the background noise from neighboring routers might be just as loud as your actual data.
Right. And if noise equals data, your throughput plummets to a crawl.
But a standard Wi-Fi analyzer is only listening for other Wi-Fi networks.
Yeah.
Right. It's only looking for traffic formatted in the 802.11 standard. What happens if the interference isn't coming from a router at all?
Then your Wi-Fi analyzer will show a perfectly clear channel, but your internet will still drop completely. To find the invisible culprits, you have to escalate to a spectrum analyzer.
Does a spectrum analyzer just look at raw radio waves across a wider frequency band?
Yeah, it looks at the entirety of the raw radio frequency spectrum, completely ignoring whether the signal is formatted as data or not.
Interesting.
The 2.4 gigahertz frequency band, which is heavily used by Wi-Fi, is notoriously crowded. A spectrum analyzer will detect non-networking devices that are flooding the environment with invisible noise.
Like what? What else is shouting on the Wi-Fi frequencies?
Microwave ovens are a classic example.
Wait, really? A microwave?
Yeah. When you turn on a poorly shielded microwave, it blasts interference across the 2.4 gigahertz spectrum. Cordless landline phones, old baby monitors, Bluetooth devices, even certain types of fluorescent lighting.
That's crazy.
A spectrum analyzer visually maps these rogue waves, proving that the network infrastructure isn't the problem, the office kitchen is.
Here's where it gets really interesting, because identifying whether the problem is in the environment, the cable, or the hardware itself is the core of troubleshooting. And the course introduces a physical tool for isolating hardware called a loopback plug.
It's a remarkably simple but powerful diagnostic tool.
At first glance, the materials make it sound a bit counterintuitive. It's a small plug you insert into a network switch or computer port, but it doesn't connect to another device.
No?
It just takes the transmit pins of the port and hardwires them directly back into the receive pins of that exact same port.
Isn't that basically like checking if your cell phone works by calling your own phone number? How does that actually help fix a network problem?
This raises an important question about how technicians eliminate variables. When packets are dropping between a server and a network switch, your biggest enemy is the unknown.
You don't know who to blame. Exactly. Is the expensive enterprise switch broken? Or is the cable running through the wall compromised? You have to isolate the suspect.
Okay, so how does the loopback plug do that?
You take the cable and the rest of the network out of the equation entirely. You take a loopback plug, which can be made for copper RJ45, serial ports, or even fiber optics, and you plug it directly into the hardware port you suspect is failing.
Got it.
Then you use diagnostic software to send a highly specific string of data out of the transmit pins.
And because the loopback plug acts as a physical U-turn, those packets immediately route back into the receive pins of that identical port.
Precisely. The diagnostic software simply compares the payload. Did the information received exactly match the information sent?
Wow. Yeah.
If it did, then the internal circuitry, the physical pins, and the port interface on that piece of hardware are working flawlessly. You've successfully eliminated the million-dollar enterprise switch as the variable.
You now know with absolute certainty that the problem is out there in the world, either in the cable or the device on the other end. We've tested the copper cables for continuity, we've tested the invisible radio frequencies for interference, and we've tested the physical hardware ports for internal failure. What if all of those tests pass, but the network is still crawling?
Then you have a bigger issue.
What if the problem is the actual data, the packets themselves getting corrupted or hijacked?
That is the ultimate escalation. When you need to analyze the actual ones and zeros flowing across a link, you have to eavesdrop on the traffic. And there are two primary methods for capturing that data: physical taps and port mirroring.
Let's start with the more invasive option. A physical tap literally requires breaking the physical connection, right? You disconnect the cable between two vital pieces of equipment, insert a specialized piece of hardware, the tap, directly in the middle, and plug everything back in.
Yeah, it acts as a middleman. For a fiber optic link, taps are usually completely passive. They contain optical splitters, essentially tiny prisms that take the beam of light carrying the data and split it into two identical beams. One continues to the destination, and the other is directed to your analysis equipment.
So no power required for fiber, it just splits the light. But copper taps are trickier.
They are. Copper taps often require a dedicated power source. They have to actively receive the electrical signal, regenerate it, and broadcast two identical copies. One down the original path and one to your capture device.
Right.
Because installing any physical tap requires taking the network offline, it is incredibly disruptive. Technicians usually schedule these installations during a maintenance window at like 2 a.m.
And what do they actually do with the copy data once the tap is installed?
They feed it into a protocol analyzer. This is specialized software like Wireshark that captures all the copied data and decodes it.
Okay, so it makes it readable.
Exactly. It translates the raw electrical pulses into readable frames and packets, allowing cybersecurity teams to look for malicious payloads or engineers to hunt for corrupted data streams.
Okay, so physical taps are disruptive to install, and copper ones might require external power. That brings us to the software alternative built right into modern enterprise switches. Port mirroring, often called SPAN, or Switched Port Analyzer.
Yeah, SPAN is a lifesaver for on-the-fly troubleshooting because it doesn't require breaking any physical connections.
How does it work in practice?
Imagine a massive network switch with 48 ports. You suspect the server plugged into port number 5 is compromised. Instead of unplugging it to install a tap, you just plug your laptop into an empty port, say port 48.
And then you tell the switch's internal software to mirror the traffic.
Right. You log into the switch and configure a rule. You basically say, take every single frame of data entering or leaving port number 5, make a silent copy of it, and forward that copy to my laptop on port 48.
So to use an analogy, a physical tap is like actually going down into the basement, slicing a water pipe in half, installing a metal T-junction, and siphoning off a sample of the water. But a span is like just having the building security camera system flawlessly duplicate the footage of the water pipe and send it to your monitor.
That's a very apt comparison. Span is non-destructive and instantaneous.
So I have to ask, if span is built right into the software, costs nothing extra, and doesn't disrupt the network at all, why would anyone ever go through the massive hassle of buying and installing a physical tap?
Well, it really comes down to processing power and the depth of the data capture.
What do you mean?
This requires understanding the difference between how a switch processes layer 2 frames versus raw layer 1 physical signals. SPAN relies on the switch's internal CPU to duplicate the traffic.
Oh, I see.
If the switch is already overwhelmed with massive amounts of network traffic, asking it to also copy everything for a SPAN session might overload its processor.
So it might just silently drop the copied frames to keep the main network alive.
It absolutely will. It will prioritize keeping the network running over sending you a copy. Furthermore, a switch only forwards valid frames.
Valid frames.
Yeah. If a network card is malfunctioning and sending physically corrupted, malformed data, the switch's hardware might just drop the bad data before the SPAN software even has a chance to copy it.
So SPAN might lie to you by omission. It only shows you the traffic the switch actually understands.
Exactly. A physical tap, on the other hand, captures everything on the wire. It copies the raw electrical signals unconditionally, including the corrupted data, the collisions, and the malformed packets.
Wow, okay.
It guarantees 100% visibility without taxing the switch's processor at all. For long-term, 24/7 cybersecurity monitoring on a highly critical link, a physical tap is the only truly secure choice.
The next time you effortlessly load a web page on your phone or complain about a video stream buffering for 2 seconds, I want you to picture the immense physical reality that is making that magic happen.
It really is an incredible fusion of manual labor and microscopic precision.
Picture the clear plastic RJ45 connectors with their tiny metal teeth permanently bitten into copper cores. Think about the plumbers of the digital world, checking those connections for cracks with continuity testers.
Right.
Picture the technicians carefully maintaining the physical twists in the wire to shield the signal, punching them into massive blocks on the walls of freezing data centers. Think about them sweeping inductive probes over thousands of cables, listening for the screech of a tone generator just to keep you online. It is profoundly physical.
It is. And if we step back and look at the broader implications of all these tools, consider this. We rely on loopbacks to test our hardware boundaries. We rely on physical twists in the copper to shield our data from the chaos of ambient electromagnetic noise, like a microwave in a break room.
Right, the analog defenses of the digital world.
Exactly. So think about this the next time you connect to the cloud. If a single untwisted inch of wire on a punchdown block or a slightly misaligned copper pin inside a plastic connector can degrade or destroy an entire enterprise connection, well, how much of our lightning-fast, highly advanced digital civilization is constantly teetering on the edge of simple analog failure?
Man, that is an incredibly grounding thought to leave on. Thank you so much for joining us on this deep dive. We will catch you next time. And until then, stay curious.